Without further ado, please help me welcome Joe. Thank you.
So thank you, Mary, for the great introduction. Thanks to everybody at Google, and also I wanted to thank my longtime colleague Terry Fong, who kind of, along with Mary, manages the NASA-Google relationship for inviting me to give this presentation. So I'm thrilled to be here. This is actually my first time on the Google campus, and so I've obviously everybody has read and heard a lot about it, but to actually see it in action is wonderful for me. I'm going to talk a little bit about the Mars Sample Return mission. It's an idea that we've had at NASA for quite some time, and we're actually ever so slowly inching our way toward executing it. And I wanted to talk particularly about the technologies that are necessary to do it. You'll see a few charts downstream. I'm going to show you all a video that's kind of an animation of Mars Sample Return, and you're going to see a few places where miracles are necessary. You'll know what I mean when you see it on the animation, and that's code for we need to develop the technology to do whatever it is that we're trying to do. So when you see that, you'll see that this mission is an incredible system engineering challenge. It's like doing Apollo with no astronauts. It even includes going to another planet, landing, doing some stuff there, launching into orbit around that planet, and coming back. So it's very analogous to what we did at the moon with Apollo, but there's no humans involved, at least not directly. And to imagine doing all the things that we did in Apollo with no humans is quite an undertaking. So without further ado, let me launch into charts. I'm going to try to run till about 45 past the hour, and Mary will give me a cue to wrap it up, and then we can have a little bit of interaction on Q&A. And I also understand there's a number of people watching this online, and I'm not sure if there's a mechanism for them to be able to ask questions, but
say they can get in touch with me.
Okay, so Mary R. at Google. If you want to ask a question and you're online, you're not in the room here. So let me go ahead and get going, and we'll work it out as we go. So a little bit of overview, and by the way, my slides are going to be graphics heavy and text light. So we can talk about the cool stuff, and I have a number of videos that I want to show you, and I'm going to. In order for me to talk comprehensively about MSR, it takes about 4 hours. And so we only have less than one. And so I've had to be a little bit selective, and instead of trying to give you a shallow view of everything, I've chosen a few things that I really want to dive in and talk about. And I think that's a better experience for you. And it's fun to talk about. And if you're still interested, I gave Mary a longer version of this presentation that has more information in it. And you're welcome to peruse that. And I have my contact information. Anyway, I'll give you a little bit of context for what we're trying to accomplish with the Mars exploration program that's instantiated at NASA now. And when I talk about Mars exploration, I'm going to talk mostly about the robotic exploration of Mars using rovers and orbiters. Obviously, there's a big effort at NASA associated with preparing for humans to go to Mars. I'll touch on that peripherally at the end of the presentation, but most of my talk is about doing this with rovers and orbiters and so forth. So talk a little bit about the context for exploration. What is it that we're trying to accomplish as a blend of science, technology, and inspiration, which I think is a product that we at NASA sometimes don't appreciate how much we're delivering that along with delivering science and technology. Talk a little bit about this Mars Sample Return mission, and then talk about some of the key technologies that include things like how we get the samples off the surface of Mars, how we kind of gobble up this thing that's the size of a basketball in Mars orbit and bring it back to Earth. I want to talk about, in particular, a really cool application for superconductors to assist us in the sort of trapping of this basketball in Mars orbit. It's called flux pinning. And then I want to talk a little bit about the fact that the Mars samples, we have a love-hate relationship with them. They're our frenemy, I guess. We want to study them. We want to bring them back to Earth and study in our laboratories. But we also have to account for the possibility that there might be biological activity in those samples, and therefore we need to treat them as if they're potentially hazard and not release these things into the Earth's biosphere until we've made sure that it's safe. And this love-hate relationship with the sample actually drives the engineering of the mission, and I'll talk more about that. And then at the end, if we do have any time, I'll talk about some of the longer-term stuff like flying helicopters at Mars and landing on a pinpoint, whereas right now we land with miles of uncertainty of where we land. land, et cetera. So that's kind of the outline. So let me talk a little bit about context, and I won't go through this point by point, but I just wanted to make the point that we, within NASA, there are sort of four major organizations that are responsible for the NASA missions. There's one that's responsible for aeronautics, so that one of the A's in NASA stands for aeronautics, even though I think NASA is much more better known for the space side. Within the space domain, we have the human exploration and operations. Those are the guys who operate this International Space Station and are preparing to send humans to Mars. There is the Space Technology Mission Directorate, which, as the name implies, is responsible for developing new technologies that can be applied across the board in NASA and beyond. And then there's what we call the Science Mission Directorate. And the Science Mission Directorate is responsible for delivering science results like you're seeing from Hubble Space Telescope, like you're seeing from the Mars Rovers. And that's the mission directorate that operates the NASA Mars missions. So we have, countless journal articles and papers and covers of Nature magazine and so forth that have resulted from the exploration of Mars. And so we've delivered a really wide variety of key science findings. Like before the Mars exploration program began, we didn't really know how pervasive water was at Mars. And it turns out that water has been extremely pervasive at Mars. In the ancient times, it was wet and warm and much more habitable for the kind of life that we are familiar with on Earth. And then something happened, and all that water went away, and Mars is now this dry, cold desert. And because Earth and Mars are kind of brother and sister in the planetary family, it would be really nice for us to understand what happened to all of that water on Mars. Why did it escape? And if you're selfish and you don't want it to happen to you on Earth, or maybe your grandchildren's grandchildren's grandchildren downstream, it would be really nice to understand that. So science is a big aspect of what we do. Engineering and technology development is another big aspect of what the Mars program delivers back to not only NASA, but to the world at large. Many of the autonomous systems that are now being implemented in driverless cars got their start as NASA tried to figure out how to operate rovers on the surface of another planet where we couldn't have direct human intervention. And Terry is one of the world's experts in that field, and I hope one day he mans up and comes and gives a talk here at Google on all of the cool stuff that he's been working on with his colleagues at Ames. Sorry for a little internal joke. Anyway, we're developing a whole variety of technologies that not only serve, sort of a localized NASA interest, like landing more stuff on Mars, which is a very specialized application, but things that help the world at large. And then the last one, and like I said, and some of my colleagues at NASA, they want to talk about the science and they want to talk about the sort of technology as applies to missions, but I think that one of our greatest products is inspiration. And for me, it was unbelievable to be at JPL the night that we landed Curiosity and to see that in Times Square was lit up with the images that were coming back from Mars. And when those the landing itself was sort of a technological achievement, but when those first thumbnail images came back and we knew we were safe on Mars, that was a human story. That was the story of all the people who threw their lives, and you guys know what this is like, to work long hours, nights, weekends, and feel like personally responsible for the success, in our case missions, in your case products, or something that Google is trying to develop. But that notion that you've invested yourself personally in something, no machine can ever take away that human inspiration. So I think that's one of the major products that we deliver. Coming back to science, there's kind of four things that organize our scientific exploration of Mars. Number one, and these are written as if they're like equals, but they're actually not. Finding life is the big one. It's the first among equals. That's the one that, if we were to find life, even microbial life, either evidence of it in the ancient history of Mars in a kind of fossilized context, or in extant life, that would be just an unbelievable change in the way in which people on Earth think of themselves and think of us as not being alone in this universe. Not to be downplayed are the other goals, like, I talked a little bit about the processes and the history of the climate on Mars. So even if you could care less about this ethereal discussion about whether or not there's life on another planet, maybe if you're a little more self-centered or thinking about the future for your kids and kids, this notion of let's not let happen to Earth what happened to Mars. Understanding how the surface of Mars evolved and the interior of Mars, that is actually vastly vastly different from Earth's. And one advantage that we have, the Earth is constantly reinventing itself. The Earth's, we have these plates, these tectonic plates that keep moving around and changing things, and there's constant upwellings in the ocean and on land, and things get recycled. So something that's been on the surface of the Earth 1 million years ago is almost certainly not on the surface of the Earth anymore. It's been somehow turned underneath. Mars is not like that. Mars has been very stable for millions and millions of years. So you have things that are on the Mars surface that have always been on the Mars surface. And from a scientific standpoint, that actually makes it a lot easier to understand the history of Mars than we enjoy here on Earth. And then the last goal from a science standpoint is preparing for eventual human exploration. And what we mean is, from a science standpoint, understand the processes on Mars that might affect human exploration, understand how the atmosphere works, understand is the surface of Mars, is the what we call regolith, which is fancy for dirt. The dirt on Mars, is that toxic to humans? That was a big question we had when the astronauts went to the moon. And it's even more likely to be an issue at Mars, that the regolith might actually include some things that are not healthy for humans to come in direct contact with. So getting ready for human exploration is a big deal. You guys probably know we've been sending rovers to Mars. You may not know that we've kind of had 3 styles of these rovers. The first one was Sojourner, which flew in 1997. It lasted about 90 days on the surface of Mars. And it operated in an area the size of this room. Never got outside of that. It only could talk back to the base station that was nearby, so if it ever got very far away, it would lose contact with the base station. And it was really a technology demonstration in 1997. So fast forward to 2004, 7 years beyond that, we send twins, Spirit and Opportunity, the Mars exploration rovers. Now those are about the size of a table, and they weigh in the neighborhood of 300 pounds each when they land. And Spirit lasted for 7 years before it got stuck in sand, and the winter came and its solar panels could no longer keep it warm, and we think it froze to death. However, Opportunity, more than 10 years later, in fact 12 years now, has gone more than 40 kilometers, so it's finished a marathon on the surface of Mars. It was only supposed to last for 90 days, and it was only supposed to go for 600 meters. And it's now gone well over 40 kilometers. So what I say is, oh, we pay too much for that system. You know, the thing should have died a long time ago. And anyway, but that's how we do it at JPL. And then finally, Curiosity, which I think almost all of you are directly familiar with. We launched it in 2011. It landed in 2012. It's still operating on Mars, and it's one of the things that proved that Mars was, in fact, a habitable place, because within its first 2 kilometers of roving, once it landed at Mars, it roved through a stream bed. And I mean, it's like absolutely no questions asked, a stream bed. So we knew that there was flowing water on the surface of Mars at some time in the past, and it was direct proof when Curiosity rolled through that stream bed. Just to give you a sense, we have not launched these guys yet to Mars, maybe sometime in the future, but I just wanted to give you some context for the size of these systems. So Sojourner, size of like a toaster oven. Curiosity, Opportunity and Spirit, the size of a table. And then Curiosity is the size of an SUV. So it weighs 900 kilograms, weighs about 2,000 pounds. And if we're going to ever send humans to Mars, we now know how to put down a Curiosity class payload. We know how to put down a metric ton onto the surface of Mars. If we're going to put humans on Mars, we need to learn how to land like 20 tons, is what a human landing system will be. So we need to increase our entry, descent, and landing capability by 20 times. Okay, so here is sort of a quickie summary of everything that's happened since the turn of the century, the turn of the millennium, 2001. We've started and we've been flying a set of rovers and we call fixed landers that stay in one place, and then a series of orbiters that perform a variety of functions. They all have scientific instruments that are looking down at Mars and asking questions about the geology, or trying to do laser altimetry so we understand what's going on in that. Some of them are looking at the atmosphere around Mars. All of our orbiters also do secondary jobs that include relaying communications from the rovers. So if the rover had to talk directly back to Earth, that's a very challenging communication link. It's a lot easier for the rover to squirt information up to an orbiter, which then can transmit the information back to Earth. So they do what we call comm relay, communication relay function. And also these orbiters, many of the recent ones, are equipped with cameras that look down and they look at places that we might choose to go in the future, and they do what we call landing site reconnaissance. So they take pictures and they say, hey, I mean, it's ironic from a safety of landing standpoint, you want to land this thing on a nice flat rock-free parking lot. But that's not where the cool science is. The science is up in the mountains. And so you have to find these areas on Mars that have both a safe place to land, but also have good science nearby. So what you want to do is you want to land in the foothills. So these reconnaissance orbiters are kind of trying to find the foothills where you have a nice safe place to land, but cool stuff very nearby is the idea. And so we've been flying these things in this mission context since 2001. A variety of orbiters. Most of them are NASA, but there's some from other countries, and including places like the European Space Agency, which is collections of countries. And then here are the rovers. And then we start to get into the future. Next year, we're going to launch one of our fixed landers called InSight, which is going to explore the interior geology of Mars. And then I imagine that you all, by virtue of being interested in space, know that SpaceX, which is a private company, is talking about going to Mars with one of their unmanned systems that they call Red Dragon, which is an adaptation of the capsule that they are delivering to the space station now to deliver crew and cargo. So they're thinking, when this chart was made, thinking about going in 2018. Just recently, they've adjusted their plan to now targeting 2020 as their first mission to Mars. And they, as you probably also know, operate in a different risk posture and a different mission cadence than NASA does. They're much more risk tolerant and they're able to execute things more quickly than we are at NASA. And so they're actually talking about going every opportunity to Mars, which comes along every 26 months. We can launch missions to Mars. So I can't wait to see what SpaceX is able to accomplish when they're in the position to be able to land on a routine basis at every Mars opportunity. Now I want to transition to the future and what's going to happen in the 2020s and beyond. We have a next Mars rover mission we call it Mars 2020. It'll get an inspirational name soon. Please send in your entries for that. But for the time being, we call it Mars 2020, which is also to pressure ourselves to launch the darn thing in 2020 and not in 2022. And then we're thinking about what's next. And then what's next is clearly and unequivocally Mars sample return. And I'll talk in the next set of slides about the fact that we need an orbiter to do that, and we need another lander that includes that rocket that I was talking about that launches the samples off the surface of Mars. And that's the decade of the 2020s. And then downstream from the 2020s is a lot more uncertain. We're not clear whether we'll have developed enough infrastructure to be serious about sending humans to Mars in the 2030s. And so we're hedging a little bit and thinking about ideas for either more robotic missions that are continuing the science exploration of Mars, or if we would transition more to supporting human missions to Mars, which would also do science, but in a different context. So we kind of have a number of pathways that we could go in the 30s. But for the 2020s, it's all about Mars sample return. Mars sample return is not a new idea at all. We've been thinking about it since the 1970s, this notion of not only going to Mars and doing in situ science with instruments that are carried on something, orbiter, rover, lander, but actually bringing samples back. And a wide variety of ways of doing that. I mean, if you defocus your eyes on what you're trying to accomplish and just say, listen, I want to get a bag of rocks back from Mars, you can think about ones that have much more elaborate roving systems, or you can think about what we call a grab sample, where you'd land and you wouldn't rove at all. You just reach down from wherever you landed and pick up a handful of this stuff and put it in the MAV and you launch. The scientists don't like that idea, by the way. They want a diverse set of samples that they have selected, not just whatever happened to be underneath the rocket when it touches down. But the thing I really love about this slide is, number one, back in the day when they were like doing these things as paintings, they still reuse things. So when you look at this one up here and this one down here, totally different concepts, but it's got the same background. So like somebody copied the background. The other thing I really love about this one is, if you see right here, here's the rover with all the samples. And then there's the MAV over there, and there's this big valley in between. And you can almost like see this question mark coming out of the head of the rover going, oh no, you're on the other side of the valley, how am I ever going to get there? So I don't know who made that painting, but they were not a Mars system engineer. they were a pure artist, but I love that. I love that picture. And as I said, a variety of different ways of doing Mars sample return. But it turns out when you do defocus your eyes and think about what it would take to bring back a sample from Mars, there's kind of 4 things that you got to do. You got to get the samples, you got to get them off Mars, you got to somehow get them, from that vicinity of Mars back to Earth, and then once you get them down here, you have to safely and while maintaining scientific integrity, you have to study them. So these 4 functions are totally independent of any particular architecture. And then, as we like to do at NASA, we like to split big problems into small problems. You start thinking about functions, and you start thinking about what elements might be able to execute. So in the color coding before, we had these 4 different things: blue, orange, green, and purple. And then you start to decompose these things into their various and sundry functions, and you start to think about specific systems that might be able to do that. So for instance, this whole thing about getting the samples. And by the way, and I'll pass it around. Here's a model of the tube that we're going to use to stick the rock cores in. And we will collect some 30-ish of these. It depends on how the mission goes. We might collect as few as 20 and can still consider it to be a mission success. But they go into this thing. So it's about the size of a cigar tube. The model I have here is a purely solid model. They're hollow for the real flight implementation, and they got all kinds of gizmos and stuff in here. But this is roughly the size of the sample. And the sample goes in the shank here, in the shaft. So in this context, we envision a rover that would collect the samples and would leave them on the surface of Mars. We're kind of like a drunken sailor, and we collect a sample and we throw it over our shoulder and we just trundle away. Actually, we don't. We put it down really carefully and we take a bunch of pictures of it from all kinds of different directions so we know exactly where it is to go back and pick up those tubes. And we pick up those tubes from another mission that flies later than this caching system that will fly in 2020 as part of the 2020 rover system. And that actually contains 2 major elements. One is another rover to go out and pick up those samples and return them to the MAV, the Mars Ascent Vehicle, which is the rocket that flies on that mission. So that mission carries a fetch rover and carries the MAV rocket. And then we have this thing so you've executed the blue stuff, you've acquired and cached the samples. You execute the orange stuff, you launch the samples into Mars orbit. Then you come and you capture that sample container, we call it the OS, and it's this basketball-sized thing. And you return it and land it on Earth, and we have a variety of different ideas on how you might land at Earth, but the most common one is that it goes splat on the desert in Utah, and protecting that sample so we don't break the egg open and let the samples out is one of the major engineering challenges associated with this. And then there's all the stuff associated with opening up the egg and getting the samples out and studying them. So let's back up for a second, and it would be complete. This was the first question that I asked when I first encountered the notion of Mars sample return over a decade ago in my career is, wait a second, why are we doing this? I mean, this is a very expensive way to study these samples. Why don't we just, if we're going to sink a lot of money into this, why don't we just sink that money into making better instruments that can get the same science that we're trying to get from our laboratories, but we do it at Mars? Well, it turns out that that's not really possible. Number one, the way that we do sample science involves very complex sample preparation that involves either hands-on or direct human-guided slicing and dicing of things and preparing specimens for spectroscopy or microscopy that we just don't have the technology today to do. So we would not be able to study them as well using an in situ instrument as we would back on Earth. Some of these instruments are still the size of rooms, and I mean, I know this is analogous to room-sized computers that now slip into your pocket, but the reality is, in terms of space exploration, we're still back in or laboratory science for analyzing the samples. We're still back in those days where the stuff that you need is the size of a room. It's not the size of an iPhone or a Google phone. Lastly, you don't always know what you want to study, and when you do it in situ, the investigations that you can do with your in situ robot is only as good as that instrument that you put on the system. Whereas if you bring a sample back, it can sit in containment for 20 years and all of a sudden you've got a new instrument that's able to do analysis that we never could do when we first flew the mission. And that's the case with the Apollo moon rocks. They're housed largely at the Johnson Space Center in Houston, Texas, and then they're distributed out to investigators. And one of the motivations for the distribution of these things are new instrument capabilities that have come along long past when those samples came back from the moon. So there's ample motivation to not try to do sample, to not try to replace the sample return mission with just in situ exploration. Here's trying to summarize this sort of 3-mission context, but actually the next video animation I'm going to show you guys is much better at doing this job. We call this a bat chart because Earth is on the bottom, Mars is on the top, and if we really did this correctly, we would be hanging the rover upside down, showing that it's all being done on Mars. But you see this sort of 3-mission thing. Mars 2020 collects sample tubes. You can fly the orbiter and the lander mission in either order. It doesn't much matter. But you have to retrieve the tubes, launch them into Mars orbit, collect them, and then bring them back to Earth. And hopefully, if this video works, I think it will.
If we want to understand the potential for life elsewhere in the solar system, our neighboring planet Mars is a great place to go. Waiting on Mars are rock samples that hold clues to whether Mars ever had an environment suitable for small life forms called microbes. Scientists would love to collect these special rocks and bring them back to study up close in laboratories here on Earth. However you tackle it, returning samples from Mars is definitely a complicated problem. But mission planners are already testing technologies to make the future possible. So how could we actually get a sample from Mars? Mission planners have several ideas. One is to build 3 different spacecraft, which would work together like a relay team. The first rover could touch down on the Martian surface and collect samples by drilling into rocks and then stashing the samples in sealed tubes. Once collected, the samples would be placed on the surface to wait for pickup by a second rover sent later. This follow-on rover would go fetch the samples, load them into a container, and bring it back to a lander with a small rocket on board. Once the container was loaded on board, the rocket would lift off, carrying the samples up into Mars orbit. Waiting in orbit would be a third spacecraft, an orbiter, that could capture the container and bring it back to Earth. With Mars samples safely back on Earth, scientists around the world will be able to study them in state-of-the-art laboratories for decades to come. The payoff of a sample return is learning about the potential for life beyond our home planet, and even whether Mars has the right environment and resources for human explorers to survive there one day.
Okay, so that's MSR in a nutshell with a few miracles mixed in. So you guys may think you have cool jobs. I got the coolest job. Okay, they pay me to develop the technologies to be able to do Mars sample return. Like I find myself on a daily basis going, I just got paid all day to think about Mars rovers, and they asked me to come back tomorrow, and they're going to pay me again tomorrow. I'm so lucky. We've had sort of 3 domains in a technology development program, and so I'm going to delve much more down into the details now of technologies to enable Mars sample return. In the 2012 to 2014 timeframe, we were really trying to get that 2020 rover enabled to be able to collect the sample. So we were working hard to develop, the drill that was going to drill the sample and not, turn it into powder, but keep it an integral core. We wanted to do what we call fast traverse, which is making it so that the rover can cover hundreds of meters per day instead of the tens of meters that we typically do with our Mars rovers today. And we also wanted to be able to land more precisely. Right now, the MSL mission, the Curiosity mission, what we call the landing error ellipse for that was about 10 kilometers by 8 kilometers. And we want to get down to much closer ones because we can, as I was saying before, we want to land close to where the good science is. So we had to, in the case of MSL, we had to rove for a couple of years before we really got to the good science. We were fortunate to encounter that stream bed on the way, but the actual intention for that mission, we didn't achieve that until we had rode for 2 years. So we're trying to be able to reduce the size of that landing error ellipse and land much more precisely. The reason that this is green here is that those technologies were developed to the level that they were able to be infused into the flight mission, and those are all being integrated into the Mars 2020 mission, and so we'll have all those capabilities that we didn't have for MSL. The stuff that's in yellow is in development now. I'm going to talk much more extensively about that in the remaining minutes that we have left to develop the MAV, to develop containment assurance, and then eventually we're going to have to develop whatever that system is that comes and lands the samples back on Earth and doesn't let the egg break open. And then way downstream we'll start developing technologies that are not related to MSR, but I'm really going to talk about MSR today. So there's a variety of technologies necessary. I've touched on a few of them already, so I won't spend too much time on this slide, but just realize many of them sort of serve more than one mission, and particularly the sense that there's 2 rovers involved in the sample return architecture. Here's what 2020 is all about. It's highly based on the Curiosity platform, so it actually looks very similar to Curiosity, and it in fact was made from some of the spares from the Curiosity mission. That's one of the ways we kept the mission costs down. But it has a completely different science package on it that's more oriented toward trying to find evidence of life on Mars and collect those samples. It looks identical, and certainly the architecture of the flight system is the same. We have this cruise stage that shepherds the vehicle from Earth to Mars. We have a back shell, which is kind of a cover that covers the good stuff inside the payload during the entry into Mars. Then we have this descent stage that you all have seen that lowers the rover down to the surface and then flies away. The rover itself kind of collapsed down into its flat condition before the wheels are deployed. And then the bottom is the heat shield. That's all the same between MSL and 2020, and it's really just the payload that's on the rover that's dramatically different. That's what it looks like when it's all put together in the clean room at JPL. And then, as I mentioned before, we have these key technologies that we infuse into the mission. So we have this model for technology development. I mean, it's really common across NASA: technology development, then infusion into a target mission application. As I said before, we're trying to narrow that landing error ellipse, and the way that we do it for 2020 that's different from MSL is we have this thing that's called terrain relative navigation. This didn't come up really in any of the sort of public discussions about Curiosity, but Curiosity really didn't know very much about where it was landing. We targeted a particular location and we did our best, the navigator did our best to put the spacecraft there, and it landed very close, landed within a kilometer of where we were targeting, which is fantastic. But we didn't have any ability to fly the vehicle in a particular direction once we actually had it underneath the parachute. It's like you pop the chute and you're going to land wherever you land. This is intending to allow you to at least adjust the direction that we go. So we come down, we take 10 quick pictures on the way down, and then we decide what direction we're going to ask the vehicle to go. And we have a divert capability that's measured in the hundreds of meters for this. So this is exaggerating the situation. It won't keep us from landing in the mountains, but it'll land us in a direction that's more safe. And then I've been alluding to this notion that we have a variety of these sample tubes we're going to lay down. We're going to fly about 40 of them. We're going to lay them in a few different locations probably if things go out the way we're thinking about it now. And we'll have what we call depots of tubes, where we have maybe 10 tubes in a not a stack, but in a line that the rover would then, the fetch rover would then go and collect. I think you guys have had a chance to see the sample tubes. This is kind of what the sample looks like inside the tube. And then we have 2 plugs and seals that are intended to keep the sample from rattling around during the reentry, and then also hermetically sealed to make sure that any of the gases or things that might be entrained in that sample don't get out. So the engineering of the sample tubes themselves, you have a very simple version of it there, but the actual sample tube is quite a complex engineering endeavor. Here are some ideas for the architecture of that we call SRL, sample return lander. It could be something that looks like the Curiosity platform, and it carries the rocket on its back. The rocket is a little bit larger than human size. It's about 3 meters in length, and it weighs, different ones have different masses, but it's in the 200 to 300 kilo range. So it's a little heavier than a human and a little taller than a human, but it's roughly that size. You could have it on your back, which is great because you're picking up tubes and you don't have to go back anywhere. You just, when you decide you have enough tubes, you finish loading them into the MAV and you launch it. Or we could have one that has a fixed platform where the MAV stays on that platform, and a smaller rover that's more the size of Spirit or Opportunity that would go out, collect the tubes, and then come back. And it's that come back part of it that has us worried and led us to think about this thing we call a mobile MAV, which is the Curiosity class. There's a variety of different autonomy and visualization technologies that are being applied. This one is a 3D augmented reality strategy that we're using, not just for to put ourselves, the operators of the mission and the scientists for the mission, on the surface of Mars, so that they can look around and say, hey, I really care about this rock, but I'd love to see it from the other direction. And using orbital imagery, we synthesize full 3D imagery of the system so that the operators and the mission planners can really have a good situational awareness of what's happening on Mars. But we've even thought about doing that for like spacecraft assembly, where when you put the spacecraft together, it's really tightly packaged, and sometimes you wish that you could just look inside and see what was going on inside there. And this is a way to synthesize the spacecraft in 3D that allow you to literally walk through the spacecraft and see what's going on there. The other one, and Terry, this is that 2-minute elevator pitch. The other one is that right now the Mars rovers, they actually roll quite slowly. We've gotten 100 meters in a day, but that's a very good day of driving, and more frequently we're getting tens of meters per day. To do this fetch operation, we're going to need a lot better performance out of the rover. It's going to have some of the driving distance is a matter of power and thermal capability of the rover to survive the cold night at Mars, but a lot of it is that we're just not smart enough to process the information quickly enough to allow the rover to drive at even a walking pace. And it would be wonderful. Right now we're getting 9 meters per day out of both MER and MSL, so it's not a matter of size even. The rovers, even though one's much larger than the other, they're both rolling along at 10 meters per day on average. We need about 4 or 5 times that level of performance, and we could get it through better automation, better autonomy, better decision making on board the rover, so it can rove and not have to stop when there's a pebble in its way. And that's a fantastic application for new technology development in the AI domain that I think would be great for this system. I talked a little bit about this basketball. We call it the OS, the orbiting sample. And what you see are those sample tubes that I passed around. We cluster them, and it turns out that when you kind of package them like a honeycomb, and you can package either 19 of them in, I think it's 4 rings, or add a 5th ring and you get up to 31. And that's what we're showing here, 31 tubes. And then that canister gets slid inside and it makes up a sphere, and you'll see in a minute why we want it to be spherical, because it makes it easier to catch it on orbit. But just know that it's about the size of a basketball. Basketball is 24 centimeters in diameter. This is 27, and it weighs about 25 pounds. So it's pretty massive, actually. And it's almost all metal of some sort, titanium and stainless steel. This is just one concept for a MAV launch where we have the platform and fetch. One of the benefits of doing this versus the mobile MAV is the fetch rover can kind of back away and watch the launch, so we get some fantastic video. And also, you wouldn't kill your rover, right? If the thing launches off the back of the rover's not likely to survive that event. So this is one advantage to the fetch and fix platform. And speaking of MAVs, we've been looking at a variety of different rocket technologies to make this possible. There's solid rockets, which are like the little Estes rockets that, as a kid, I hope you played with. There are what we call bipropellant rockets, which are analogous to the space shuttle or what SpaceX is launching now, where you're mixing together a fuel and an oxidizer. The hybrid is kind of halfway in between. It has a solid fuel, but either a liquid or a gaseous oxidizer. And it turns out for the Mars application, this hybrid is just right because we have problems with the solids cracking when they descend and they have to encounter the landing environment that we have. It's also, they're not very good at cycling thermally, hot to cold during the day, and the hybrid fuels don't have that problem. So we're looking at a hybrid implementation for the MAV. That was the landed system. Here is the orbiter system that would collect the sample. It has big solar arrays because it actually uses what we call solar electric propulsion rather than using chemical rockets to propel itself. We use solar power to heat up an ionized gas that then gets ejected out the back and is a much more efficient power source. And this thing called ROX is the package that captures the sample. I want to talk a little more about that. So the ROX system, this basketball is in Mars orbit, and it's inert. Okay, it has no propulsion system. So what we do is with the orbiter, we chase it down and we close in on it, and we actually finally rendezvous with it in the last sort of 100 meters. We close down, and that basketball gets put into some sort of a system that captures it and contains it. And I'm leading you to another technology that I wanted to show you. We have to then either encapsulate it because it might have Mars material on the outside. Remember, we have to treat that Mars material as potentially hazardous. And then because we're so afraid of it, we actually do it twice, and we do two encapsulation exercises. And then we release that encapsulated system somehow, either in the form of a reentry capsule that lands on the surface, or there's other ideas. And we've been looking at a whole variety of different alternatives to how we do this rendezvous and capture it. Some are very sort of, let's call them conventional mechanical things, where you fly this thing kind of into a basketball net. That's this one here. And then you close a lid and you drive it through the system. There's another one that I want to show you in a second that's really cool. There's the OS coming into the system. This one actually uses mechanical arms to come and trap the OS. Then, this is all still attached to the spacecraft. We just deleted it so you can see what's going on. We reoriented because we care what orientation those samples land on. We don't want them to land with the seal down and be driven through the seal. So we want them to kind of lay flat when they land on the Earth's surface. Here we're brazing. Brazing is like soldering. It's kind of welding the two halves of the container that the OS is in. Then it moves into this thing that we call the EEV, Earth Entry Vehicle. And we do one other layer of containment there, so we have a second layer, and you'll see this sort of hangar door thing flip open, and then the EEV gets ejected. And that's the whole sequence of everything that happens. Punch it off, and there you go. So I wanted to talk about a really neat technology called flux pinning. The scenario that I just showed you before, we capture that OS with mechanical arms. This one uses superconductors and magnets. And it turns out that there's a style of superconductor, type 2 superconductor, that if you take it through its transition temperature, at higher temperatures, these things just are sort of inert pieces of metal stuff. And then if you cool them down, in this particular class, it's below 80 degrees Kelvin, they become superconductors. And it turns out that if you do these type 2 superconductors, if you take them to a transition temperature in the presence of a permanent magnet, they set up flux fields. And these flux fields are what allow you to levitate this. This is just a regular permanent magnet, nothing special about this one. It wants to stay in place there. As long as you hold that superconductor below its critical temperature, in the presence of the magnetic field, it wants to pin that magnet in place. And that turns out to be extremely valuable for what we're trying to do on the Mars sample return. So we have an idea that we could try to characterize this well in order to be able to use it to capture the OS and hold it and orient it in proper position. So In this context, the OS would have these permanent magnets on the outside of the thing, and it would fly into the spacecraft. And then using superconducting magnets arrayed in this pattern, we could actually control the orientation of the OS. So we not only would capture it using the superconductors, we actually could turn it into a preferential orientation and then trap it down. And I wanted to show you just a couple of videos from a flight. Here's an operation at Cornell on a flat table. But I'll also show you an operation we just did in March on a microgravity aircraft. We flew this thing because on the flat table you only get 3 degrees of freedom, right? It goes X and Y and you can get yaw, but you're not getting all 6 degrees, Z, pitch, yaw, and roll. So we actually flew this on the microgravity airplane where, let's see, there we go. That was day one before the guy learned don't try to swim. So you get, on one of these parabolas, you get about 20 seconds of hang time, but you really only get about 3 or 4 seconds of good 0G. So let me just show you. This is from a camera that's mounted on the frame. That's my hand there. So you see how it, just for a couple of seconds, got pinned in there. Everybody was really jazzed. Here's a particularly good run. If anything happens, if you touch anything in the plane, you're no longer together and the Oscar's flying out. So you'll see how far we actually translate in the plane in 0G. So we do get to have some fun every once in a while. And we're thinking about flying this on the space station in a couple of years, and then eventually in Mars. This is simulating the landing of that Earth entry vehicle on the desert floor at 3,000 Gs. And that's on a muddy, it could rain in the desert, and we're testing on what happens when it lands in mud. And what it does is it just creates this huge splatter of mud. So I'm showing you the fun stuff, right? I'm not showing you me sitting in meetings all day long and developing budgets and schedules. I'm showing you when we get to fly on the microgravity plane or when we get to make the mud go splat. Okay, so downstream after this we have big ideas about other systems that could explore Mars, helicopters, balloons, landing more things, and eventually getting ready for humans. So sorry for the fast close there, but if you're really interested, please ask Mary for the slide package and you can look at it in more detail, and I'm happy to talk with you offline. All right, thank you very much. I know I hit you with the fire hose, but thank you very much.
I'm wondering, with the sort of idea of the magnetic capture, sort of, firstly, does that have a long enough range to be practically useful in orbit? It feels like it would be range constrained more than a basket. And sort of, secondly, what were the reasons to use superconducting methods instead of active control with a regular electromagnet to accomplish that task?
Sure. So first, two fantastic questions. Number one, it would be beautiful if this tractor beam acted over kilometers and it was just like in Star Trek, but it acts over centimeters. The good news is we can control the spacecraft to single-digit centimeters. So I can fly that retrieval system up to the OS within about 5 centimeters. So I only need that tractor beam quality to actuate over single-digit centimeters, and it does. That's that aspect, the really important thing is that we do it without contacting, without getting a lot of dust flying off of the OS and contaminating the spacecraft. That's the big advantage over the conventional mechanical means, is we never actually touch the OS in this scenario. It comes in and it pins in that equilibrium condition with no contact to the spacecraft. And we're able to orient the OS without touching it. And it turns out that this orientation function is winding up being a big design. I didn't think it would be when we first embarked on this thing, but it turns out that orientation is a big design driver for the mechanical systems. The second one is, why do we do it with superconductors rather than just regular conventional magnets? You could, but that potential well and that pinning capability in the equilibrium position is a lot more difficult to synthesize with electromagnets. It wants to drive right into contact with the magnet and stick in contact. Now, you can levitate electromagnetically, but it's a lot harder than this, which does it passively. So as long as you keep that superconductor below its critical temperature, as long as you're keeping it that cold, you don't have to do anything else. You don't need an elaborate control system. It just operates that way, as long as you pin the magnet in place. So yes, you could do it with electromagnets, but the superconductors have a number of characteristics that are beneficial. That passive equilibrium position, the non-contact case, et cetera, those things make it advantageous. The downside is it's a low technology maturity right now, and so we're inventing the technology as we go, whereas people have much more experience, obviously, with electromagnets and conventional permanent magnets. So those things are in tension in our development. Thank you, that's a super question.
I actually had a similar question, but I'll go with a different one because you answered my first one. I'd like to know a little bit about the relationship between NASA and SpaceX and how much coordination there is between the two organizations and how much competition there might be.
Yeah, another great question, and I'm going to do my best to be candid, but with a little bit of diplomacy. So, number one, as I mentioned to you, I'm really, really impressed with all the things that SpaceX has been able to accomplish. We, especially at JPL, but NASA Ames also has a relationship with SpaceX. We're helping them do some of the things that they really can't do for themselves. Like, for instance, we're talking with them about some of the really technical aspects of the entry, descent, and landing environment so that they understand some of the lessons that we learned the hard way without having to repeat them. And so we're providing them with some engineering support as they develop their system. And there's other areas where they're not looking for that support. They think they have the answer, and they may even have the personnel that have the experience that are able to give them that. So we're supporting them in some very particular engineering domains in areas where NASA has clear expertise that SpaceX does not have. In return, there are discussions between SpaceX and NASA about returning the favor in the form of landing things for us, because we're only getting opportunities to land on the Mars surface every half a decade or so. If they're going on every opportunity, it'd be wonderful if we could put payloads onto their system. So there's a bit of an interchange, and there are motivations on both sides for that relationship. One thing I can say is that I think SpaceX is really changing the paradigm. They certainly have done it in the launch vehicle game, and I anticipate that as they spread into other domains like spacecraft, satellites, like for Mars applications, they're going to change the paradigm in the way that they did for launch vehicles. They're going to change the paradigm in those other domains. I happen to be somebody who thinks that those paradigm changes are good for the ecosystem as a whole. So I'm really a huge fan of SpaceX. And I think most people that you talk to at JPL and Ames have sort of a similar perspective.
So I'm somewhat curious if there's been any lessons learned from rover attempts of like other countries, and because most of what we see is coming from NASA or maybe SpaceX, but we don't see much coming, at least publicized from the other countries.
Right. In the domain of Mars exploration, particularly when we talk about landing things on Mars and using them on Mars, the U.S. is kind of the only player that's been successful. We actually have one of the slides that I didn't show you guys today is we have a scorecard of attempts versus successes, and it's like 39 attempts and 15 successes, and almost all of those successes are U.S. No other country has successfully landed something on Mars that lasted for more than a few seconds. The Russians landed something that died in a matter of seconds. the only country that's ever had anything that really delivered science back from the surface of Mars is the United States. Now, that's not to say that we don't have wonderful collaborations with other international partners like the European Space Agency that are providing things on the instrument level. And they're now getting to the point of trying to do things like rovers. The Europeans are planning to launch a rover mission in 2020 that would sort of look like Spirit and Opportunity in terms of its ambitions for size and roving distance and so forth. But no one's really yet been successful at the, let's call it the mission level, other than NASA. So right now the collaborations are at the instrument level, but the mission level, we're still waiting for them to catch up.
I'm wondering why you have the second rover at all. I mean, if you just kept all the things on the first rover, and you say the rocket that's coming is going to be able to land, on a dime, why not just land next to it?
Yeah, I guess I'm never going to get an easy question from you guys. Very insightful question, and yes, you could do this with one single landed element, but let me explain technical motivations and also allude to some programmatic motivations. Technically, the mission that it's going to take to collect those samples is going to take a couple of years on the Mars surface, and while we've had great success. Spirit lasted 7 years. Opportunity is 12 years. Curiosity is now in its, sixth year of operation. We can't count on those super long mission durations, particularly the solar powered systems. If they ever get themselves in a condition where they're sort of stuck and they can't point their arrays at the sun over the winter, the Mars winter, they freeze to death. So we're very reluctant to bake into our mission planning multi-year missions. And we think that collection process is going to take a couple of years. And so it kind of eats up the amount of time that we're willing to allocate to a single mission. The collection operation actually takes less time than the sample I'm sorry, when I say collection, I mean the fetching operation of collecting the sample tubes from the surface. It takes much less time than the drilling of the cores and laying those samples down on the surface. And we're just nervous that that's too much to pack into one single mission. That's the technical explanation. There's a programmatic explanation that says we're sending the Mars 2020 mission to Mars to do a fantastic in situ mission, which, by the way, stands on its own. We would send that system, I believe, regardless of whether or not there was a sampling package on it. But it's great that we have the sampling package and we get started on Mars sample return. And we build some momentum that says, hey, Congress and the Congressional Budget Office, we have 33 sample tubes lying on the surface of Mars. They have unbelievable science locked inside them. Please, let's go get them and bring them home. That's a compelling story that gets to be told starting in 2021 when the 2020 rover lands, rather than betting on the come and sending that mission in 2027, 2028 and hoping that you have good samples. So the opportunity to get started soon, have something that's compelling to bring back, helps to motivate the rest of the missions. So I told you a technical story and I told you a programmatic story. Both of those combined are why we have separate missions for caching and return. We could conceivably do it on one mission, but it makes more sense to do it in two. Yeah, so the question, for those of you who couldn't hear, the question was, do these two rovers that are participating in sample return, do they have a mission after they've completed their sampling responsibilities? And the answer, certainly in the case of 2020, the answer is an emphatic yes. As I said before, it has an instrument package that's doing in situ science in addition to the sampling operation. That in situ science can happen before you collect samples, while you're collecting samples, after you collect samples. And after I just told this story that we're afraid the rovers aren't going to last very long, the reality is they do. In practice, they last for a long time. And we anticipate after we finish that sample caching mission, if the rover is still going strong, we would continue the science mission. The one that's a little bit more sort of not clear at this point is the fetch rover. And as I showed you on that one image that showed the MAV launch where we had a small fetch rover that could stand off from the MAV launch and observe it from a safe distance. That one we expect that hopefully the rover would survive that MAV launch and go on to do more science. The mobile MAV, where you're carrying the MAV on your back and you put it into its launch orientation and off it goes, that one probably trashes the rover. And we've been thinking about ways to maybe put the rocket off the back of the rover so it's not thrusting directly down onto it. But that fetching mission, also the amount of science instrumentation that we would be able to put on that system, which is already doing the MAV roll and everything, it's a much more questionable thing. So I think 2020 is going to do a good ancillary science mission, irregardless of the sampling operation. The ability of the fetch rover to continue to do more science is questionable. So that's playing into the architecture of the missions.
Okay, so Brian wants to know, how are you planning to get the necessary amount of maneuvering capability to rendezvous with the OS, given that the vehicle uses an ion drive?
Great. 5 for 5. Someone asked me why Mars is red or something like that. Please, send me a softball and I could smash out of the field. Now, we'll actually augment that ion thrusting system with a cold gas thrusting system specifically for the purpose of doing the rendezvous function. We could not execute the rendezvous purely with the low thrust engines that you have when you're doing ion thrusting. So it'll be cold gas, either hydrazine or maybe even xenon. That was the pressure, that was the gas that we're blowing out of the ion thruster. We might be able to use some spare xenon for that function. It turns out in practice, hydrazine packs a much more powerful punch, and so it's better for us to use hydrazine as the fluid, but we would not try to do it with the ion engines. We'd do the rendezvous with a cold gas or hydrazine system.
Is there any consideration to having more than one sample returning vehicle, for example, collecting more samples opportunistically, and if we were able to collect more, then send another mission like in next 5 years?
Right, so the question was, is there perhaps a motivation to have multiple sample returns, either from the sample set, I'm going to extend a little bit on your question, either from the samples that we take from 2020 or multiple sample return missions themselves? The answer is yes. We're going to carry, right now the plan is to carry a little more than 40 of these sample tubes, and we'll collect as many as we can, and we'll lay as many on the surface as possible. My guess is that none of them are going to be such duds that we would not want to bring them back, right? There's going to be a fantastic scientific debate on whether we bring back sample 2, 4, 6, 9, et cetera, which ones we bring back. But we're most likely not going to be able to bring back every single tube that we collect. So there would be a strong motivation to want to return all of those tubes. Furthermore, we're only going to be able to land at one site and do science in that one location. And while we're trying to pick landing sites that have a diversity of potential scientific return, it is only one place. And just like on Earth, it's not the same thing to vacation in Hawaii as it is to vacation in Finland. And so we would want to go to other places on Mars and return samples from multiple locations. That, of course, would require a different mission to do the sample collection and caching. Also, as you can tell from what I've described to you so far, we're making a rather large investment in the technology for this, and it would be great to see it amortized over multiple missions rather than just one singular one. So we can envision multiple sample return missions, either to finish the job if there's still good samples left from the first mission, or to have multiple sample returns flown from different landing sites, different sample suites.
So now that we have pretty strong evidence that there was historical flowing liquid water on Mars, would that have potentially impacted kind of the coloration of the planet such that the red planet was not historically red?
That's a hard question masked as an easy question. So I'm not kidding. You've stumped me more with that question than with all the previous ones that have come. The red planet's red because it's iron oxide in the soil. That's why it's red. The presence of liquid water didn't really affect the fact that this iron oxide exists on Mars. I think that's not necessary. The water's not necessary for that iron oxide to form. So the connection between color and presence of water. I may have a scientific colleague who's going to make my phone buzz in a second saying, no, you're wrong. But I think that those are relatively disconnected phenomena. Thanks. So, thank you again.